What if I told you everything around you exists because atoms don't stay stable on their own? Your phone, water, even your own body. All of it is made because tiny particles decided to connect. But here's what nobody tells you in school. Atoms don't bond because they want to. They bond because they're desperate. Desperate to fill a hole. Desperate to reach stability. And in that desperation, they build literally everything around you. The water in your glass. The screen you're watching this on. The DNA twisting inside every single cell of your body. Today, we're going deep into chemical bonding. And by the end of this video, you'll never look at the world the same way again. First of all, we need to look inside an atom to understand everything. An atom has a nucleus at the center and electrons moving in shells around it. You can imagine these shells like layers. But here's the important part. The outermost shell, called the valence shell, decides how an atom behaves. Scientists observed something interesting. Atoms become very stable when their outer shell is completely filled. For most atoms, that means having 8 electrons. This idea is known as the octet rule. Think of it like needing 8 hours of sleep. Some atoms come close. Most don't. Let's compare 2 cases. Neon, its outer shell is completely filled, making the atom stable and mostly non-reactive. Take sodium, for example. It has only 1 electron in its outermost shell, which makes it highly unstable. So naturally, it tries to change its configuration to become more stable. So what does sodium do? It tries to get rid of that 1 electron. Now, take chlorine. It has 7 electrons in outer shell. Needs just 1 more. So chlorine tries to gain an electron. Now imagine this situation. Sodium wants to lose an electron and chlorine wants to gain an electron. Perfect match, right? Sodium gives 1 electron to chlorine. And just like that, they form a bond. This type of bonding is called ionic bonding, where atoms completely lose or gain electrons. But what if atoms don't want to fully give away or take electrons? They share electrons. This creates a different type of bond called covalent bonding. So now we have 2 main ways atoms bond. Bond by transfer of electrons and other is by sharing of electrons. But metals do something completely different. In a metal, atoms don't bond to specific neighbors. Instead, they release their outer electrons into a shared pool, like a sea of electrons that flows freely through the entire solid. This is the metallic bond. And it's the reason metals have their unique properties such as electrical and thermal conductivity, malleable, and ductile. That's why you can bend gold into jewelry or draw copper into thin wires. The electron sea just adjusts. So far, we have talked about chemical bond, but even after these big 3, the story doesn't end there. Molecules still attract each other through invisible forces called intermolecular forces. The hidden reason behind liquids, solids, surface tension, and even why water droplets form. These forces are weaker than chemical bonds, but absolutely critical. Now, among all intermolecular forces, one of the most important is hydrogen bonding. But what makes hydrogen bonds so special? When hydrogen is bonded with highly electronegative atoms like oxygen, nitrogen, or fluorine, the electrons are pulled strongly toward those atoms. This creates a strong partial positive charge on hydrogen and a partial negative charge on the other atom. Without these bonus attractions, water would be a gas at room temperature and life as we know it wouldn't exist. Hydrogen bonds are constantly forming and breaking between water molecules, giving it that cohesion. It's also why DNA works. The 2 strands of the double helix are held together not by covalent bonds, but by hydrogen bonds between base pairs, strong enough to hold the code of life together, weak enough to unzip when the cell needs to copy it. But do you know, not all intermolecular forces are that much strong. At the weaker end, we have van der Waals forces, the weakest intermolecular attractions, caused by temporary random fluctuations in electron distribution. Every molecule has them. They're how geckos walk on walls. Millions of tiny van der Waals interactions between their toe pads and the surface add up to enough grip to defy gravity. Hence, from the strong hydrogen bonds in water to the tiny van der Waals attractions between molecules, intermolecular forces silently control the behavior of matter all around us. So, the next time you drink water, taste salt, or hold your phone, remember, you're holding trillions of atomic agreements that took billions of years of cosmic evolution to perfect. Chemical bonds aren't just chemistry, they're the reason anything exists. In this series, we'll break everything down step by step: ionic bonding, covalent bonding, Lewis structures, molecular shapes, and much more. If you enjoyed this, drop a like, comment your favorite bond type below, and subscribe for more science that actually matters. Hit the bell, because the universe has way more secrets to share. I'll see you in the next one. Stay curious.